Good morning, and welcome to Optimizing Swift Performance. My name is Nadav, and together with my colleagues, Michael and Joe, I'm going to show you how to optimize your Swift programs. Now, we, the engineers on the compiler team, are passionate about making code run fast. We believe that you can build amazing things when your apps are highly optimized. And if you feel the same way, then this talk is for you. Today, I'll start by telling you about some of the new compiler optimizations that we've added over the last year. Later, Michael will describe the underlying implementation of Swift and give you some advice on writing high-performance Swift code. And finally, Joe will demonstrate how to use instruments to identify and analyze performance bottlenecks in your Swift code. So, Swift is a flexible and safe programming language with lots of great features like closures and protocols and generics and, of course, automatic reference counting. Now, some of you may associate these features with slowness because the program has to do more work to implement these high-level features. But Swift is a very fast programming language that's compiled to highly optimized native code. So, how did we make Swift fast? Well, we made Swift fast by implementing compiler optimizations that target all of these high-level features. These compiler optimizations make sure that the overhead of the high-level features is minimal. Now, we have lots of compiler optimizations, and we don't have enough time to go over all of them. So I decided to bring you one example of one compiler optimization. This optimization is called bounce checks elimination. On the screen, you can see a very simple loop. This loop encrypts the content of the array by XORing all of the elements in the array with the number 13. It's not a very good encryption. The reading and writing outside of the bounds of the array is a serious bug. It can also have security implications. And Swift is protecting you by adding a little bit of code that checks that you don't read or write outside of the bounds of the array. Now, the problem is that this check slows your code down. Another problem is that it blocks other optimizations. For example, we cannot vectorize this code with this check in place. So we've implemented a compiler optimization for hoisting this check outside of the loop, making the cost of the check negligible. Because instead of checking on each iteration of the loop that we're hitting inside the bounds of the array, we're only checking once when we enter the array. So this is a very powerful optimization that makes numeric code run faster. OK, so this was one example of one optimization. And we have lots of optimizations. And we know that these optimizations work and that they're very effective because we are tracking hundreds of programs and benchmarks. And over the last year, we noticed that these programs became significantly faster. Every time we added a new optimization, every time we made an improvement to an existing optimizations, we noticed that these programs became faster. Now, it's not going to be very interesting for you to see all of these programs, so I decided to bring you 5 programs. The programs that you see on the screen behind me right now are programs from multiple domains. One is an object-oriented program. Another one is numeric. Another one is functional. And I believe that these programs represent the kind of code that users write today in Swift. And as you can see, over the last year, these programs became significantly faster, between 2 to 8 times faster, which is great. Now, these programs are optimized in release mode. But I know that you also care about the performance of unoptimized programs, because you're spending a lot of time writing your code and debugging it and running it in the simulator, so you care about the performance of unoptimized code. So these are the same 5 programs, this time in debug mode. They're unoptimized. So you're probably asking yourself, wait, how can improvements to the optimizer improve the performance of unoptimized code, right? Well, we made unoptimized code run faster by doing two things. First of all, we improved the Swift runtime component. This is the component that the runtime is responsible for allocating memory, accessing metadata, and things like that. So we optimized that. And the second thing that we did is that now we're able to optimize the Swift standard library better. The standard library is the component that has the implementation of array and dictionary and set. So by implementing this, by optimizing the standard library better, we're able to accelerate the performance of unoptimized programs. Okay, so we know that over the last year, the performance of both optimized and unoptimized programs became significantly better. But to get the full picture, I want to show you a comparison to Objective-C. So on the screen, you can see two very well-known benchmarks. It's Richards and Delta Blue. They're both written in object-oriented style. And on these benchmarks, Swift is a lot faster than Objective-C. Now, at this point of the talk, I'm not going to tell you why Swift is faster than Objective-C, but I promise you that we'll get back to this slide and we'll talk about why Swift is faster. Okay, now I want to talk about something different. I want to talk about a new compiler optimization mode that's called whole module optimization that can make your programs run significantly faster. But before I do that, I'd like to talk about the way Xcode compiles files. So Xcode compiles your files individually. And this is a good idea because it can compile many files in parallel on multiple cores in your machine. And that's good. It can also recompile only files that need to be updated. So that's good. But the problem is that the optimizer is limited to the scope of one file. With whole module optimization, the compiler is able to optimize the entire module at once, which is great because it can analyze everything and make aggressive optimizations. Now, naturally, whole module optimization builds take longer, but the generated binaries usually run faster. In Swift 2, we made two major improvements to whole module optimizations. So first, we added new optimizations that rely on whole module optimization mode. So your programs are likely to run faster. And second, we were able to parallelize some parts of the compilation pipeline. So compiling projects in whole module optimization mode should take less time. On the screen behind me, you can see two programs that became significantly faster with whole module optimization because the compiler was able to make better decisions. It was able to analyze the entire module and make more aggressive optimizations with the information that it had. In Xcode 7, we've made some changes to the optimization level menu. And now, whole module optimization is one of the options that you can select. And I encourage you to try whole module optimization on your programs. At this point, I would like to invite Michael on stage to tell you about the underlying implementation of Swift and give you some advice on writing high-performance Swift code. Thank you.
Thanks, Nadav. Today, I'd like to speak to you about three different aspects of the Swift programming language and their performance characteristics. For each, I will give specific techniques that you can use to improve the performance of your app today. Let's begin by talking about reference counting. In general, the compiler can eliminate most reference counting overhead without any help. But sometimes you may still find slowdowns in your code due to reference counting overhead. Today, I'm going to present two techniques that you can use to reduce or even eliminate this overhead. Let's begin by looking at the basics of reference counting by looking at how reference counting and classes go together. So here I have a block of code. It consists of a class C, a function foo that takes in an optional C, and a couple of variable definitions. Let's walk through the code's execution line by line. First, we begin by allocating a new instance of class C and assign it to the variable x. Notice how at the top of the class instance, there is a box with the number 1 in it. This represents the reference count of the class instance. Of course, it's 1 because there's only one reference to the class instance currently, namely x. Then we assign x to the variable y. This creates a new reference to the class instance, causing us to increment the reference count of the class instance, giving us a reference count of 2. Then we pass off y to foo, but we don't actually pass off y itself. Instead, we create a temporary c, which then we assign y, and then we assign y to c. This then acts as a third reference to the class instance, which then causes us to increment the reference count of the class instance once more. Then, when foo exits, c is destroyed, which then causes us to decrement the reference count of the class instance, bringing us to a reference count of 2. And then finally, we assign nil to y and nil to x, bringing the reference count of our class instance to 0, and then it's deallocated. Notice how every time we made an assignment, we had to perform a reference counting operation to maintain the reference count of the class instance. This is important since we always have to maintain memory safety. Now, for those of you who are familiar with Objective-C, of course, nothing new is happening here, with, of course, increment and decrement being respectively retain and release. But now I'd like to talk to you about something that's perhaps a bit more exotic, more unfamiliar, namely how structs interact with reference counting. Let's begin this discussion by looking at a class that doesn't contain any references. Here I have a class point. Of course, it doesn't contain any references, but it does have two properties in it, x and y, that are both floats. If I store one of these points in an array, because it's a class, of course, I don't store it directly in the array. Instead, I store a reference to the points in the array. So when I iterate over the array, when I initialize the loop variable p, I'm actually creating a new reference to the class instance, meaning that I have to perform a reference count increment. Then when p is destroyed at the end of the loop iteration, I then have to decrement that reference count. In Objective-C, one would oftentimes have to make simple data structures like point a class, so you could use data structures from Foundation like NSArray. Then, whenever you manipulated this simple data structure, you would have the overhead of having a class. In Swift, we can use structs. In Swift, we can work around this issue by using a struct in this case instead of a class. So let's make point a struct. Immediately, we can store each point in the array directly, since Swift arrays can store structs directly. But more importantly, since a struct does not inherently require reference counting, and both properties of the struct also don't require reference counting, we can immediately eliminate all the reference counting overhead from the loop. Let's now consider a slightly more elaborate example of this by considering a struct with a reference inside of it. While a struct itself does not inherently require reference counting modifications on assignment like I mentioned before, it does require such modifications if the struct contains a reference. This is because assigning a struct is equivalent to assigning each one of its properties independently of each other. So consider the struct point that we saw previously. It is copied efficiently. There are no reference counting needed when we assign it. But let's say that one day I'm working on my app and I decide that, well, I would like to make each one of my points to be drawn a different color. So I add a UI color property to my struct. Of course, UI color being a class, this is actually adding a reference to my struct. Now this means that every time I assign this struct, it's equivalent to assigning this UI color independently of the struct, which means that I have to perform a reference counting modification. Now, while having a struct with one reference count in it is not that expensive, I mean, we work with classes all the time, and classes have the same property. I would now like to present to you a more extreme example, namely a struct with many reference counted fields. Here I have a struct user, and I'm using it to model users in an app I'm writing, and each user instance has some data associated with it, namely 3 strings, one for the first name of the user, one for the last name of the user, and one for the user's address. I also have a field for an array in a dictionary that stores app-specific data about the user. Even though all of these properties are value types, internally they contain a class which is used to manage the lifetime of their internal data. So this means that every time I assign one of these structs, every time I pass it off to a function, I actually have to perform 5 reference counting modifications. Well, we can work around this by using a wrapper class. Here again, I have my user struct, but this time, instead of standing on its own, it's contained within a wrapper class. I can still manipulate the struct using the class reference, and more importantly, if I pass off this reference to a function, or I declare, or I initialize a variable with the reference, I'm only performing 1 reference count increment. Now, it's important to note that there's been a change in semantics here. We've changed from using something with value semantics to something with reference semantics. This may cause unexpected data sharing that may lead to weird results or things that you may not expect. But turns out there is a way that you can have value semantics and benefit from this optimization. If you'd like to learn more about this, please go to the Building Better Apps with Value Types talk in Swift tomorrow in Mission at 2:30 p.m. It's going to be a great talk. I really suggest that you go. Now that we've talked about reference counting, I'd like to continue by talking a little bit about generics. Here I have a generic function min. It's generic over type T that conforms to the comparable protocol from the Swift standard library. Well, from a source code perspective, this doesn't really look that big. I mean, it's just 3 lines. But in reality, a lot more is going on behind the scenes than one might think. For instance, the code that's actually emitted, here I'm again using pseudo-Swift to represent the code the compiler emits. So the code the compiler emits is not these 3 lines. Instead, it's this. First, notice that the compiler is using indirection to compare both x and y. This is because we could be passing in 2 integers to the min function, or we could be passing in two floats or 2 strings, or we could be passing in any comparable type. So the compiler must be correct in all cases and be able to handle any of them. Additionally, because the compiler can't know if T requires reference counting modifications or not, it must assert additional indirection so that it can handle, so that the min_t function can handle both types T that require reference counting and those types T that do not. In the case of an integer, for instance, these are just no-op calls into the Swift runtime. In both of these cases, the compiler is being conservative since it must be able to handle any type T in this case. Luckily, there is a compiler optimization that can help us here, that can remove this overhead. This compiler optimization is called generic specialization. Here, I have a function foo. It passes 2 integers to the generic min_t function. When the compiler performs generic specialization, first it looks at the call to min and foo and sees, oh, there are 2 integers being passed to the generic min_t function here. Then, since the compiler can see the definition of the generic min_t function, it can clone min_t, and then specialize this clone function by replacing the generic type t with the specialized type int. Then, the specialized function is optimized for int, and all the overhead associated with this function is removed. So all the unnecessary reference counting calls are removed, and we can compare the 2 integers directly. Finally, the compiler replaces the call to the generic min_t function with a call to the specialized min_int function, enabling further optimizations. While generic specialization is a very powerful optimization, it does have one limitation, namely the visibility of the generic definition. For instance, in this case, the generic definition of the min_t function. Here we have a function compute, which calls the generic min_t function with 2 integers. In this case, can we perform generic specialization? Well, even though the compiler can see that 2 integers are being passed to the generic min_t function, because we're compiling file1.swift and file2.swift separately, the definition of functions from file2 are not visible to the compiler when the compiler is compiling file1. So, in this case, the compiler cannot see the definition of the generic min_t function when it's compiling file1, and so we must call the generic min_t function. But what if we have whole module optimization enabled? Well, if we have whole module optimization enabled, both file1.swift and file2.swift are compiled together. This means that definitions from file1 and file2 are both visible when you're compiling file1 or file2 together. So basically, this means that the generic min_t function, even though it's in file2, can be seen when we're compiling file1. Thus, we're able to specialize the generic min_t function into min_int and replace the call to min_t with min_int. This is but one case where the power of whole module optimization is apparent. The only reason that the compiler can perform generic specialization in this case is because of the extra information provided to it by having whole module optimization being enabled. Now that I've spoken about generics, I'd like to conclude by talking about dynamic dispatch. Here I have a class hierarchy for the class pet. Notice that pet has a property noise, has a method noise, a property name, and a method, the noise impl, which is used to implement the method noise. Also notice that it has a subclass of pet called dog that overrides noise. Now, consider the function makeNoise. It's a very simple function. It takes an argument p that's an instance of class pet. Even though this block of code only involves a small amount of source again, a lot more is occurring here behind the scenes than one might think. For instance, the following pseudo-Swift code is not what is actually emitted by the compiler. Name and noise are not called directly. Instead, the compiler emits this code. Notice the indirection here that's used to call namesGetter or the method noise. The compiler must insert this indirection because it cannot know, given the current class hierarchy, whether or not the property name or the method noise are meant to be overridden by subclasses. The compiler in this case can only emit direct calls if it can prove that there are no possible overrides by any subclasses of name or noise. In the case of noise, this is exactly what we want. We want noise to be able to be overridden by subclasses in this API. We want to make it so that if I have an instance of pet that's really a dog, the dog barks when I call noise. And if I have an instance of pet that's actually a class, that when I call noise, we have a meow. That makes perfect sense. But in the case of name, this is actually undesirable. This is because in this API, name is never overridden. It's not necessary to override name. We can model this by constraining this API's class hierarchy. There are two Swift language features that I'm going to show you today that you can use to constrain your API's class hierarchy. The first are constraints on inheritance, and the second are constraints on access via access control. Let's begin by talking about inheritance constraints, namely the final keyword. When an API contains a declaration with the final keyword attached, the API is communicating that this declaration will never be overridden by a subclass. Consider again the makeNoise example. By default, the compiler must use indirection when it calls the getter for name. This is because without more information, it can't know if name is overridden by a subclass. But we know that in this API, name is never overridden. And we know that in this API, it's not intended for name to be able to be overridden. So we can enforce this and communicate this by attaching the final keyword to name. Then the compiler can look at name and realize, oh, this will never be overridden by a subclass, and the dynamic dispatch, the indirection, can be eliminated. Now that we've talked about final and inheritance constraints, I'd like to talk a little bit about access control. Turns out in this API, pet and dog are both in separate files, pet.swift and dog.swift, but are in the same module, module A. Additionally, there is another subclass of pet called cat in a different module, but in the file cat.swift. The question I'd like to ask is, can the compiler emit a direct call to noise impl? By default, it cannot. This is because by default, the compiler must assume that this API intended for noise impl to be overridden in subclasses like cat and dog. But we know that this is not true. We know that noise_impl is a private implementation detail of pet.swift, and that it shouldn't be visible outside of pet.swift. We can enforce this by attaching the private keyword to noise_impl. Once we attach the private keyword to noise_impl, noise_impl is no longer visible outside of pet.swift. This means that the compiler can immediately know that there cannot be any overrides of noise_impl in cat or dog because, well, they're not in pet.swift. And since there's only one class in pet.swift that implements noise_impl, namely pet, the compiler can emit a direct call to noise_impl in this case. Now that we've spoken about private, I would like to talk about the interaction in between whole module optimization and access control. We've been talking a lot about the class pet, but what about dog? Remember that dog is a subclass of pet that has internal access instead of public access. If we call noise on an instance of class dog, without more information, the compiler must insert indirection because it cannot know if there is a subclass of dog in a different file of module A. But when we have whole module optimization enabled, the compiler has module-wide visibility. It can see all the files in the module together. And so the compiler is able to see, well, no, there are no subclasses of dog. And so the compiler can call noise directly on instances of class dog. The key thing to notice here is that all I needed to do was to turn on whole module optimization. I didn't need to change my code at all. By giving the compiler more information, by allowing the compiler to understand my class hierarchy with more information, I was able to get this optimization for free without any work on my part. Now I'd like to bring back that graph that Nadav introduced earlier. Why is Swift so much faster than Objective-C on these object-oriented benchmarks? The reason why is that in Objective-C, the compiler cannot eliminate the dynamic dispatch through OPC message send. It can't inline through it. It can't perform any analysis. The compiler must assume that there could be anything on the other side of an OPC message send. But in Swift, the compiler has more information. It's able to see all the certain things on the other side. It's able to eliminate this dynamic dispatch in many cases. And in those cases where it does, a lot more performance results, resulting in significantly faster code. So please use the final keyword in access control to communicate your API's intent. This will help the compiler to understand your class hierarchy, which will enable additional optimizations. However, keep in mind that existing clients may need to be updated in response to such changes. And try out whole module optimization in your release builds. It will enable the compiler to make further optimizations, for instance, more aggressive generic specialization, and by allowing the compiler to better understand your API's class hierarchy, without any work on your part, you can benefit from increased elimination of dynamic dispatch. Now I'd like to turn this presentation over to Joe, who will show you how you can use these techniques and instruments to improve the performance of your application today.
Thank you, Michael. My name is Joe Griswack. I'm an engineer on the instruments team, and today I want to take you through a quick demo application that's running a little slowly right now. So let's get started. All right, so here we have my Swift application that's running slowly. So what I want to do is go ahead and click and hold on the Run button and choose Profile. That's going to build my application in release mode and then launch instruments as template chooser so we can decide how we want to profile this. Since it's running slowly, a good place to start is with the timed profiler template. From instruments, just press record. Your application launches, and instruments is recording data in the background about what it's doing. So here we can see we're running at 60 frames per second before I've started anything, which is my target time with target performance. But as soon as I add these particles to the screen, they're moving around and avoiding each other just like I wanted. But now we're running at only about 38 frames per second. So we lost about 1/3 of our performance. So now that we've reproduced the problem, we can quit our application and come back to instruments. Let me make this a little bit larger so we can see what's going on. You can just drag this Drag that around. View snap track to fit is handy to make the data fill your horizontal time. And now what are we looking at? Here in the track view, this is our CPU usage of our application. We can see here on the left where I did anything, CPU usage was low. After I added those particles, CPU usage became higher. You can see what those values are just by moving your mouse and hovering it inside of this ruler view. And we can see prior, we were at around 10% or so, not doing much. Later on, we moved up to around 100%. So we kind of saturated our CPU. So in order to increase our performance, we're going to need to decrease how much work we're doing. So what work were we doing? That's where this detail pane down below comes in. So here's all of our threads. I can go ahead and open this up a little bit. And you're probably familiar with this call stack from seeing it inside of Xcode in the debugger. Start, calls main, calls NS application main, et cetera. But what Instruments is also going to tell you is how much time you were spending inside of that function, including its children, right here in this first column running time. So we can see 11,220 milliseconds, or 99% of our time, was spent in NS application main, or the things it called. The second column self is how much time Instruments sampled inside of that function itself, so it excludes its children. So what I want to do is see where does that self number get larger, and that means that function's actually performing a lot of work. You can continue opening these up one by one, hunting around, but that can take a little while. Instead, we recommend you come over here to the right side, this extended detail view, and Instruments will show you the single heaviest stack trace in your application. So that's where it sampled the most number of times. You see again, here's our main thread. It took 11,229 milliseconds. It began in start. Symbols in gray are system frameworks. Symbols in black here, like main, are your code. And what I'd like to do is just look down this list and see if there's kind of a big jump. That means something interesting happened around this time. So if I scan down this list, the number's slowly getting smaller, but there's no big jumps going on until I get down here, where I see a jump from about 9,000 to about 4,000. So something happened there. So I'm going to go ahead and just click on my code. And Instruments has automatically expanded the call tree on the left side so you can see what you just clicked on. All right, so let me frame this up. And what's going on here? Well, if I back up just a little bit for a moment, here's my NSFire timer call. So that's what's driving my simulation, trying to get at 60 frames per second. And down here is my particlesim.appdelegate.update routine. That's my Swift routine driving the simulation. But in between is this weird @objc thing sitting there. I just want to point out that's just a thunk. Basically, it's a compiler inserted function that gets us from the Objective-C world here in NSFire timer down to the Swift world down here inside of my code. That's all it is, otherwise we can ignore it. Now, we can see my update routine is taking 89% of the time, so continuing to optimize this function is a good idea. So everything else above it's not really interesting to me. So I'm going to go ahead and hide it by focusing in on just this update routine by clicking this arrow here on the right. Now, everything else around this has been hidden. Our running time here has been renormalized to 100% just to help you do a little less mental math. And if we look in what's going on in this function, update phase avoid calls find nearest neighbor, and that calls down into something really interesting here. We see Swift release is taking 40% of our time, and Swift retain is taking another 35% of our time. So between just these two functions, we're doing about 3/4 of our update routine is just managing reference counts. Far from ideal. So what's going on here? Well, if I double click on my find nearest neighbor routine that calls those retains and releases, Instruments will show you the source code. However, Swift is an automatic reference counted language, so you're not going to see the releases and retains here directly. But you can, if you go over to the disassembly view, click on that button there, Instruments will show you what the compiler actually generated. And you can hunt around in here and see there's a bunch of calls here. There's 23% of the time on this release. There's some more retains and releases here. There's another release down here. They're all over the place. So what can we do about that? Let's return to our code here and go to my particle file. Here's my class particle. So it's an internal class by default. And it adheres to some collidable protocol. All right. Down below this is the find nearest neighbor routine that was taking all of that time before. Now, I know that when the update timer fires, that code's going to call find nearest neighbor on every single particle on the screen. And then there's this inner for loop here that's going to iterate over every single particle on the screen. So we have an n² algorithm here, or effectively, the stuff that happens inside this for loop is going to happen a really large number of times. So whatever we do to optimize this thing should have big payoff. So what is going on? Well, we have our for loop itself where we access one of those particles. So there's some retain release overhead. There are property getters being called here, this .id property. And as Michael was talking about, since this is an internal class, there might be some other Swift file somewhere that overrides these property getters. And so we're going to be performing a dynamic dispatch to these property getters, which has retain release overhead as well. Down here, there's this distance squared function call. And despite the fact that it lives literally a dozen source code lines away, once again, we're going to be doing a dynamic dispatch this routine with all of that overhead as well as the retain release overhead. So what can we do about this code? Well, this code is complete. I wrote this application, I'm finished, my particle class is complete, and I have no need to subclass it. So what I should do is communicate my intention to the compiler by marking this class as final. So with that one little change, let's go ahead and profile application again and see what happened. This time, the compiler was able to compile that file knowing that there are no other subclasses of that particle class, excuse me. And that means it's able to perform additional optimizations. It can call those functions directly, maybe even inline them, or any other number of optimizations that can reduce the overhead that we had before. So if we record, this time when I add the particles, we can see they're moving around and they're running around at 60 frames per second this time. So we got back 20 frames per second with just that one small change. Now that's looking good. However, as you may guess, I have a second phase here called collision, where we swap out the algorithm and now they're bouncing off one another. And again, our frame rate dropped by about 25% down to 45 frames per second. So we've reproduced the problem again. Let's return to instruments and see what's happening. So we'll do what we did before. Make this a little bit larger, snap track to fit. And now what do we see? So over here on the left, this was our avoidance phase. Things are running much better. They're running around 30, 40% or so. So that's why we're hitting our 60 frames per second. But over here on the right, this is our collision phase. And now this is capping out at 100% of our CPU. And that's why our frame rate's suffering again. So if we did what we did a moment ago, right now, this call tree data down here in the detail pane is going to have data from this avoidance phase, which is running fine, as well as this collision phase, which is what I really want to actually be focusing on. And so that avoidance samples over here is just going to kind of water down our results. So instead, I would like to set a time filter so I'm only looking at my collision phase. And that's really simple to do. Just click and drag in the timeline view. And now our detail pane has been updated to only consider the samples from our collision phase. Now we can do what we did before. Let's head over to our extended detail view. Look down this list, see where we see it jump. And something interesting happens here. We went from about 8,000 milliseconds to 2,000 milliseconds. So I'm going to click on my collision detection class here. Instruments, once again, automatically expands this call tree for us. And if we just kind of look at what's going on here, 88% of my time is spent inside of this run time step routine. So this is a good place to dig in. I'll do what I did before and click on this focus arrow here on the right. Now we're looking at just our run time step routine. And let's see what it's doing. All right, well, 25% of its time is being spent inside of swift.array._getElement. When you see this A inside of angle brackets, that means you're calling into the generic form of that function and all the overhead that that entails. You'll see this again here inside of Swift array is valid subscript. There's that A inside of angle brackets. And it also happens when you have that A inside of square brackets, so we're calling a generic property getter here. So just between these three generic functions, we're looking at about 24, so about 50% of our time is being spent inside of these generic functions. So what can we do about getting rid of that overhead? All right, back over to Xcode. Here's my collision detection file. Here we can see that collidable protocol that my particle was adhering to. And here's that generic class detection of type T that adheres to a collidable protocol. What does it do? Well, it has this collidables array here that's of generic type T. And here down below is our run time step routine. And that's where we were spending all of our time. So what does this function do? Well, it iterates over all our collidables. It accesses one of the collidables from that array, calls a bunch of property getters here. Here's some more. There's an inner for loop where we do kind of the same thing again. We pull out a second collidable from that array, and then all sorts of property getters down below. So we're doing a lot of generic operations here, and we'd really like to get rid of that. So how do we do that? Well, this time, you can see my collision detection class is here inside of this Swift file. However, the users of this, where where I'm using this class is inside of this app delegate routine, this particle Swift file. So it's in other parts of this module. So we're going to have to turn to whole module optimization. Doing that's really easy. Just click on your project. Let's go over here to build settings. Make sure you're looking at all of your build settings, and then just do a search for optimization. And here is that setting that Nadav showed you earlier. You just want to switch your release build over to whole module optimization. And now when we profile, the compiler is going to look at all those files together and build a more optimized binary. But let's check and see what happened. So we'll launch Time Profiler for the third time here. Start our recording. And 60 frames per second. We add our particles. This avoidance phase still running at 60 frames per second. Good. I expected that not to change. Always good to verify. And then we move over to our collision phase. Now that is running at 60 frames per second as well. And all it took was a couple minutes of analysis and a few small tweaks, and we made our application a lot faster. All right, so to summarize what we saw here today, we know that Swift is a flexible programming language that that's safe and uses automatic reference counting to perform its memory management. Now, those powerful features are what make it a delight to program in, but they can come with a cost. And what we want you to do is focus on your APIs and your code that when you're writing them, you keep performance in mind. And how do you know what costs you're paying for? Profile your application inside of instruments and do it throughout the lifetime of your application development so that when you find a problem, you find it sooner and you can react to that more easily, especially if it involves changing some of your APIs. There's documentation online, of course, the developer forums where you can go, and you'll be able to ask questions about Swift and get them answered, as well as instruments. And speaking of instruments, there's a profiling in-depth talk today in Mission at 3:30. There's an entire session devoted to Time Profiler and getting into even more in-depth than we were able to get into today. And as Michael talked about earlier, there's a building better apps with value types in Swift that'll also build upon what you saw today. So thank you very much.